Hello, today I wanted to show you how to make an operating system, or at least how to start an operating system with aarch64 and Rust. So we start by doing a cargo new, let's call it my tut.os, and let's just run it for now. So what did we do? When we ran this, it runs it on our Linux machine. This is a Linux machine right now, and we get a binary. We have this, and we see that it's for GNU Linux 370. This is not what we want, because if we use a system emulator or a bare metal target, we do not have an operating system running, which means that our code is basically the first thing that runs on the processor. To make Rust know that we want to run this on a what's it called, on another processor, we need another target. We need to make a folder called .cargo and give it a config.toml file. And in the config.toml file, we can specify our build options and a target. So what would this target be? If most of you probably installed Rust up, if we go for Rust up target list, we see all of these targets. So we see 3, for example, we're gonna use aarch64 in this case. This is the processor architecture. Like, we got aarch64, we got ARM 32-bit, ARM v7, i686 or x86 64, and what we're interested in are the aarch64 things. Then we have the vendor, which in this case would be Apple, for example, Linux, PC, and unknown. And the third one is the operating system that it's going to run on. So, which means this one runs on Mac OS, which is Darwin, iOS, Android, Windows, Fuchsia, and so on. But what we're interested is actually aarch64 unknown none, because we don't have an operating system at all. So let's actually grab that and put it in here. Like this. Okay, now we told Rust, or rather Cargo, to build our operating system for a aarch64 target. Let's try to build it. And now it complains about various stuff. It can't find the crate for std, it cannot find the macro for print line, panic handler is missing, requires a lang item. Let's start from the top. It tells us what we need to do. So it can't find std, so std is required because it does not declare no standard. The standard library is operating system dependent, and since we don't have an operating system at all, we cannot even use it. It specifies things like how to write to the screen. In Linux there's a syscall called write, and we use that to write to the terminal, to the screen, or whatever file descriptor that you want to write to. We don't have any of that, so we need to declare or create as this is not what I wanted to do. What I actually wanted to do was this one, as no standard. And then let's try building it again. Next thing is we cannot find println. The same thing, it's operating system dependent how to print. So what we're gonna do is we're just gonna loop forever for now. Then it says I cannot find a panic handler. A panic handler is in Rust when your program crashes. For example, you write out of bounds, then your panic handler is called. That it can print you a message, hey, I had a problem, I'm gonna terminate the program now, or whatever you want. And let's call this panic and leave it empty for now. So now it's gonna complain, okay, I found your panic handler, but it's of the wrong type. We actually need this type. Let's grab this type real quick. and put it in here. The lifetimes are not really important to us right now, and it also mentioned that it should never return. So this bang, this return type with the bang means do not ever return from this function. Now, since we never return, if we now try to compile it, it's going to complain that it expected never return but found the unit type. That is because if you leave a function empty, it's gonna return the unit type automatically. Okay, now we got this, and we need to, of course, name the info. Let's call it info for now, and put an underscore since we're not using it. Okay, not found in the scope. This is easily fixed by importing it. And now we imported it, and now it says, okay, function main requires a standard library. To use to do this, we need to use no main. The no mangle part we're gonna not do right now, because we expect our operating system to be the very first thing that runs. And since Rust requires for function calling a stack to be present, which is not the case if we are really the first code that ever runs, we're gonna ignore this right now. So we're gonna define our own start function that actually uses assembly to initialize the stack before we call into Rust code. Okay, now we do a cargo build. Of course, I made a mistake. This one needs to go up here. No main. Okay, now it builds. Now we have another problem though. If we try to object dump this to see what code it generated, we will see that it did not generate any code. Why is that? Because now we don't have an entry point. And to tell the compiler where the code goes, or rather the linker where the code goes, we need to define a so-called linker script. So to do that, we are going to first go into cargo and the config.toml where we specified our build target, and we're going to add a line. We're going to add target dot and then our target name, and here we're going to do Rust flags equals, and here we're going to put link dash arc dash t, and we're gonna call it linker.ld. Actually, we're gonna put in source linker.ld. So what this is gonna do is it's gonna instruct the Rust compiler to pass this to the linker, and so that it can use the linker script to decide where our code snippets end up. To make a linker script, we're gonna go to source linker.ld, and we're gonna start with one thing, which is the entry point of our function. The entry point we're actually gonna call underscore start. This is gonna be our assembly code. That's the first thing that runs, and then we will have sections. So in the sections we have multiple sections that we need. We have .text, we have .data, we have row data, and we have .bss. Okay, here we need to put a colon and okay. Okay, let me format this real quick. Oh my god, I'm so bad. Okay, there we go. Okay, so the next thing that we say, we defined our entry point up here. And since we need our entry point to be the first instruction in the binary, we're gonna say keep this entry point, keep everything that matches text underscore start. Okay. And then we're gonna say the rest, put the rest of the text section after it. That's that. Here in data, we just wanna put the .data segment everything. Row data, the same thing. .row data, and here, and then here the same thing for .bss. Good, that should allow our code to compile for now. Yes, and if we object dump this whole thing, we're gonna see that it still didn't do anything. The reason here is now we did not define our underscore start function, so it doesn't know where to find it. To do this is what we're gonna do is we are going to go into source main, and we're gonna do a global ASM, which means a global ASM means that we are not defining this at the function levels, but instead it puts this function anywhere in the binary. And here we will include a string, and we're gonna call it boot.s. Okay, and now in source boot.s, we are going to define our underscore start function. So our underscore start function is gonna start with the section that it goes in. So we put it into text underscore start. Then we're gonna define this function as global, and we give it the type of underscore start function. Okay, then we put our label here, and then we need to put our code here. So what code do we need to put here? We need to initialize the stack and then call into main. So the call into main is very easy. We just branch with link, call main. To initialize the stack, we need to load an address and then store it to the stack pointer. The way we're gonna do this is we are going to make use of Rust's features. So what we're gonna do is we are actually going to define our stack in Rust right now as a static. So we're gonna do a static mute stack as an array of U8s, and we're gonna make our stack, let's say 2 megabytes or something. 2 megabytes big. Or actually, let's make it like 1 kilobyte for now. Let's make it 1 kilobyte, and it's gonna be 0 initialized with 1 kilobyte. So now we have a static. Now we need to put it somewhere into the binary. So we're gonna do a link section equals, let's call it dot stack for now. And we also do not want to mangle this, so no mangle. And on this one we also want to do no mangle. No mangle is important because by default Rust gives every function a let's say a random name. It's not completely random, but it's a unique name. And this unique name is going to cause us problems when we want to call it from assembly. So what we're gonna do is we say with no mangle, do not give this a unique name, just call it stack, just call it main. Okay, so what we can do in global ASM is we can actually define variables that we want to pass in. So we can say there's a symbol called stack, and we want to have this symbol. Oops, that's not what I wanted to do. What we're also gonna do is we're gonna have a let's make it a const, which is stack size, and this is also gonna be a usize, which is gonna be 1024 bytes, and this will do the same, const stack size. We have it like this. Actually, let's not make it const, let's make it a normal static. Otherwise we need to enable feature flags, since this is currently unstable. Okay, now we can go ahead and say in our assembly we want to load something from the .stack. How are we gonna do this? The best way is, I guess, we will define in our linker script the .stack section. I would just put it here for now. Okay. And then we say we keep our stack variable and we keep everything in the stack segment. Yes, okay, and that should work for now. Now we go into our boot.rs and we will want to set up the stack by doing an ADR to load something. Let's load it into x7 and choose the first argument in the in our ASM call. If we recall, we have a main.rs. Our first argument is our actual stack, and the second is the stack size. So what we're gonna do is we put the address of the stack into x7, and then we move our x7 into the stack pointer. Now this would probably already work, but this would be a bug because a stack grows from a high memory address into a low memory address, which means to get the real stack, we need to need to actually add to x7 and our third argument, which we would move into x8 for now. And now we move the stack pointer. So again, move stack address of stack variable, move the stack size into x8, and then we add that to the stack. Actually, do we want to add or subtract? We want to add into the SP, and then we move it into the stack pointer. After that, we will call into main, and that should be it. Let's try to build this right now. Okay, it complains we need to use global ASM. We're gonna do that. main.rs, we're gonna use it. Okay, cargo build. Oh, okay. This is not how you do comments in assembly like this. It means it thinks that it is a literal. Okay, we still got this mangled, which is not good. We will do the same on this variable. So this is why it's important that we have a no mangle. Invalid fix up. Okay, so we want to use a LDR instruction, I assume. X8. Okay. This one I didn't get into now, like I didn't encounter this when I wrote my code. So let's just do it the way that I did it. In my code, we're gonna do make this a const and enable the feature gate for asmconst. Okay. Now this should compile. Okay. Rust up, toolchain, no, rust up default. Okay, make it the nightly toolchain. That's why it's important to make it the nightly toolchain. And we need to remove no mangle on this. And now we compiled it. Now if we object dump, we see that we have our start function and then our main function. Since we're gonna write, put this all into QEMU, I'm gonna write a little serial driver thingy, which is just gonna write an A to the address that is needed. So let's see, uart base was this one as star mute u8, and then we have unsafe. We are going to write to this pointer dot write volatile, and we want to write an A as u8, of course. Okay, let's object dump this again. Now we have a lot more code in here. Let's do a less, and let's see, we have this, we have the start function, we have somewhere our main function, there we go, and here we have the address for the serial port, and it's gonna write volatile to it. Okay, so we do a cargo build, and now the next step that we need to do, since this is an ELF file, source, no, it's target, aarch debug my.os. So this is an ELF file. QEMU cannot easily load L files. So what we actually need is a project called give me a second, cargo bin utils. So yeah, the project that we need is called cargo bin utils. Cargo bin utils, and to install it, what we do is we do a cargo install bin utils. I already installed it here, but then also we need to do a RustSwap component at LLVM tools, which contains stuff like object copy, which we need. And what we're gonna do now is we're gonna do a Rust object copy dash capital O binary target aarch64 my.os, and we're just gonna put it into my.os.o. So what happened now is, now it's just data, and if we see my.os, we see there are some bytes, object dump dash d less my.os. Yeah, oops, I made a mistake. Like this, of course. And we want capital D for disassemble everything. Oh, okay, it cannot. Okay, whatever. But believe me, the code is in there. Next step that we need to do is use QEMU system aarch64 with give it 1024 memory, give it in Cortex A72, I guess, or do we do 75? That's 76. Let me look real quick. 76. We are going to use the vert board, and now the important part, we're using serial monitor, and serial is going to go to standard IO. We're going to use no graphic, and another important thing is the device that I'm adding now. Device will be a loader at adder. We're gonna just put it at this arbitrary address, like RAM starts at this address in QEMU, but I'm just gonna put it here for now. Then we say CPU dash num equals 0, and then we specify our file. File equals my.os.o. And this should print an A if we did everything right. But it seems like we didn't do everything right. So what's going on? To figure that out, what we can do is we can put SS to say stop execution at the start, and open a GDB server. And then we can go into my.os on a second monitor, and say rust gdb my.os.o target mode 1234 and layout ASM layout rex. And now we can step through it and see what it's doing. So it's gonna move our address in x7, x8, adds them together. Then it's gonna put it into the stack pointer, which is now gonna have the same address. We're gonna get into main. We're gonna put something on the stack, put something on the stack. We're gonna subtract the stack. We're gonna put something on the stack. Put an address in here. Put more things on the stack. Store the byte. And then we do a bunch of stuff, and we end up in an exception. Okay, so we end up in an exception, probably because of write volatile. So what I'm gonna do is I'm just going to forgo write volatile for now, and gonna say or star uart adder equals hex 41 of it, which is a capital A. And this should probably cargo build this and do the object copy again, this one, and run it. Now, okay, now it looks like it did it. And we see we have an A here. Okay, and let's make a function to just write hello world real quick. So we're gonna use this window for now. Main, we're gonna do a fn serial put char with which takes a character, and this is going to write to this uart address in the exact same manner. Okay. Yeah, this is not working anyway, so let's get rid of this and save. Okay. And let's just leave it like this for now. And this character is going to be our input here. So it's going to be C as U8. And here we want to do a serial put char. And let's put a B here for now. Exactly the same thing. We're gonna do cargo build, copy the object, and we see a B. Now we can take this further. Now that we have a one char method, we can actually do a serial put string, which takes an let's call it S for now, a reference to a string. And with that reference, we're gonna call for let's see, for character in, what was it, character in here, for character in s.chars. We iterate over every character. We are going to call serial put char with the character. And like this, we should be able to say serial puts hello world. And now we have a hello world. And this is basically how you write hello world in Rust when you want to write an operating system. And let's recap this real quick. So what we did is the first entry point is of course our global ASM. So we're gonna go to boot S. We're loading the stack and just jump into Rust code. And then from Rust code, we are in main. We call serial puts and put char. What we had to set up besides that was, of course, the stack size or panic handler. And that's basically it. What we could also do now is we can have a real panic handler. We can say serial puts panic, and then we're just gonna call the panic macro for now let's not have any message. We're building this, we're copying, and it still says hello world. Wait a second. Cargo clean, cargo build, object copy, and this. It still does the hello world for some reason, but yeah. Let's see if this works. Oh yeah, of course it does it. Because we still have it in there. But why does it not panic? Anyway. Even if it doesn't panic, we at least have our hello world, and yeah, that's basically it. So if you have any questions, please leave a comment. If you have any suggestions on how to make this better understandable, or what I could do to teach you in a maybe more visual way or whatever, then leave your suggestions in the comments and I'll try to figure something out. Anyway, thank you for watching, and I hope this showed you a little bit into how to start an operating system, how to also debug an operating system, and what all of this is about, how to set up your toolchain. Thank you for watching.